and welcome to this engineering and mechanics tutorial on differential connections. In this tutorial, we will look at a very simple case and just see what we need in order to inform the differential connections and plot the graphs for the shear force and the bending moment diagram. So this is the first example that we are going to solve using differential connections. You can see that it's a simply supported beam with a pin support and a roller support and a uniformly distributed load of 12 kilonewtons per meter. The length of the beam is 9 meters, and we've been asked to find the shear force and bending moment diagrams using differential connections. Now, the first thing that I'm going to do is solve the reactions, and since we already know how to do that, I'm just going to replace these two supports with the reaction, which is, of course, 54 kilonewtons on either side, because this is symmetric, and you can either do this by looking at symmetry and doing 12, which is the force, times 9 divided by 2, because each of these will have to be equal, or by solving, for example, moments around one point and finding the same reaction. The next thing I'm going to do is just under this beam, I am going to leave a place for my shear force and for my bending moment, and just putting the units in here. And that's it, we are ready to begin. So the first thing I note is that the uniformly distributed load is 12 kilonewtons per meter. I start off by writing down the differential connection for the shear force, which is a function of x. And it is the integration of minus w minus the load dx. In our case, we have minus 12 dx, and as you know, the integration of a constant or of a number is just that number, so minus 12 times x. Now, I need to not forget the constant of integration, so plus c1. Now, the value of this constant depends on the boundary conditions. So in our case here, we know that when x equals 0, the shear force equals 54 kilonewtons, right? Because at 0, we only really have the reaction force, right? The UDL hasn't really influenced yet. So we know this. And knowing this, we can integrate it into the equation that we just found. So S, the shear force when x equals 0, equals minus 12x plus c1. And since x equals 0, that means it just equals c1, right? Because this term of x equals 0. And as we just noted, from our prior knowledge, that equation needs to equal 54. So we have found out that c1 equals 54. And now we can write that back in our shear equation and see what our final equation is for shear. So S of x equals 54 minus 12x. I've just rearranged it so that the minus comes second. And that equation gives us shear anywhere on the beam. So I can plot it now and find out what the shear force is. So I can see that when x equals 0, I start with 54. So let's draw that there. When x equals 4.5, so when I'm in the middle of that beam, if you calculate that, that works out as 0. And when x equals 9, so I'm at the other end of the beam, I can see that x is minus 54, and therefore my shear force diagram looks like this. Now I want to find the moment. I'm just going to write here the shear force because I will need to use that. And that is because the differential connection for moments states that mx equals an integration of Sx of the shear force dx. So now I need to integrate the shear force, so 54 minus 12x, according to dx. And if I do that, I start off with a constant once again, so that becomes 54x. And then I have minus 12 times an integration of x, which is x squared over 2. and obviously another constant of integration, so plus C2. So just rewriting that, so it's a bit nicer, 54x minus 6x squared plus C2. So once again, I have another constant of integration and I need to find what that is. Now in this case, I definitely know that when x equals 0, the moment has to equal 0, right? Because it's a simply supported beam. So at the support, there's no restraint for moment, and therefore the moment is 0. So if I put that into my equation, so if I say m when x equals 0 equals 54x minus 6x squared plus c2, and as you can already tell, this first bit and this second bit, they're both 0. I'm left only with C2, and that all needs to equal 0, right? And therefore, C2 equals 0. And therefore, the equation for moment, mx, is 54x minus 6x squared. And I can plot that as well. If I do, I can see that when x equals 0, I'm here. When x equals 4.5, I get 54 times 4.5, which is 243, minus 6 times 4.5 squared, which is 121.5, and that gives me 121.5 kilonewton meters. So that is the moment here. And when x equals 9, I get 54 times 9, which is 486, and minus 6 times 9 squared, which as we expect is also 486, giving us 0, which is exactly what we expect. Now we can see according to this that we have x squared, so we know this is going to be a parabola, and it's going to look something like that. Should be nice and symmetric. And we can see according to these equations, so this is the final equation for moment, and this was the equation for shear, we can tell from these equations what we expect the shape of the function to look like. So we can see that the shear is a function of x, which means it's going to be a linear line, and the moment is a function of x squared, which means it's going to be a parabola. We can also see, as we know from before, that when the shear force passes through 0, then the moment is at the maximum. Now in this case it is symmetric, and so we know exactly where that location of maximum is. But say we didn't, we can find it out easily, and I will show you how next. So say I wasn't too sure where the maximum moment was, okay? So we'll start off by finding the location of max moment. Now we know that the maximum moment happens when the shear force equals 0. So we're going to say the shear force is 54 minus 12x. When that equals 0, we know we have the max moment. So let's solve this. We have 54 equals 12x. So x equals 54 divided by 12. And that is, unsurprisingly, 4.5 meters. And then obviously to find the maximum moment, I need to take the moment equation and substitute x equals 4.5 into it, because I know that is the location of the maximum, and we've already solved this, so we know this is 121.5 kilonewton meters. But this method will work regardless of the equations used. And that's it. We have found the shear force diagram and the bending moment diagram using differential connections, and we've also shown how we would find the location and the value of the maximum moment. Thank you for joining me. I hope you found this tutorial on differential connections helpful, and I hope it helped you put everything we discussed theoretically into practice. Join me later for some more engineering mechanics, and in the meanwhile, practice, practice, practice.